How are you everyone? I hope that all of you are doing very well. So today we will go through the practice problems and the practice questions for chapters 13 and 14. I will make sure to explain those problems and questions very well and their answers as well. So let's get started, and I'm going to start now with the practice questions for chapter 13. So let's go through these questions together. So as you can see right here, we have a simple question. So this simple question tells me which of the following best defines temperature. Okay, so we did some of these questions in the classroom, but I will go through them again. Okay, so let's do that. So for temperature, the best definition for temperature: the total energy of all particles in a substance, the measure of average kinetic energy of particles, the potential energy stored in a material, the total number of particles in a system. So the right answer, guys, is B. So why is that? Because the material or the gas, for example, as you know, it has like small particles, as you can see right here. So if we increase or decrease the temperature for the material, so what will happen? The thing that can happen, the average kinetic energy of all of these gas molecules or particles is going to change. We know that the temperature actually is defined as we have right here from the thermal kinetic energy. We have 3/2 Boltzmann constant times temperature is equal to half mass V squared. And here, guys, you can see that we are talking about average kinetic energy, so we are considering the average kinetic energy for each one of these gas particles or gas molecules. Okay, so you can see the link now between temperature and the average kinetic energy from the relation between thermal kinetic energy and mechanical kinetic energy. Okay, average mechanical average kinetic energy. So that's great. Let's now move to number 2, and in number 2 you can see that at thermal equilibrium, what is true for two systems in contact. Okay, so A, they exchange no heat and have equal temperature. B, they continue to exchange heat forever, which is impossible. The hotter object absorbs more heat. The colder object emits more heat. So you can see from this key word, which is equilibrium, you can see that that there is no like heat exchange anymore. So you can see A is the right answer. According to the 0th law of thermodynamics, if we have two objects, object A and object B, and they are in contact, you will see that after they achieve the equilibrium, they will have the equilibrium temperature. Okay, and both of them will have this final temperature, and there is no heat exchange anymore once those two particles achieve the equilibrium situation. Okay. I'm going now to move to number 3. So let's do now number 3. So in number 3 here, let's read number 3 carefully and see what do we have. So number 3, if the temperature of a gas changes from 100 Celsius to 200 Celsius, by what factor does its Kelvin temperature increase? Here the key is very simple. So the factor here is the key. So we just need to convert from Celsius, from 100 Celsius to Kelvin, and from 200 Celsius to Kelvin. So what I'm going to do now, so just to let you know that the screen is in front of me right now, that's why I'm looking this side, but I will keep eye contact with you guys. So we have here 100 plus 273.15. That's going to give me the Kelvin from 100 Celsius, and I have here 200 plus 273.15, and that's going to give me the Kelvin from the 200. Let's have a calculator and calculate them. So I'm going to extract a calculator. Here is a calculator, guys. So I have here 100 plus 273.15. That's going to give me 373.15. And I believe the other one also is easy, so it's going to give me like 473.15. So I think the good idea is to just divide the 473 by 373 and see what we will get. So that's going to give me the factor. So let's do that. It will clean everything here. So I will do 473.15 divided by 373.15. So that's equal to 1.26, as you can see. So the closest number here is C. So C is the right answer. Okay. So we just need to write here that the answer for this is 373.15 Kelvin, and from here we have 473.15 Kelvin. So to get the factor, what do we need to do? So to get the factor, we need to divide the 473.15 Kelvin divided by 373.15 Kelvin, and that's going to give me 1.26 as a factor. Okay, so this is the right answer, but you can see the closest number here is 1.24. Okay, and that's going to give me like how much the temperature is increasing. Okay, so that's very good. Now let's move to number 4 and see how can we do number 4. So which statement about temperature scales is true? So let's see those statements and see. So we have scale here. So A, the scale is from Celsius to Fahrenheit. B, the scale is from Kelvin to Celsius. The scale here is from Celsius to Kelvin, and the scale here in D is from from Fahrenheit to Kelvin. So let's now see. So when we have Celsius and Fahrenheit, so there is no equal change, guys. Okay, so the change is not equal, and you can see that from this equation, which is T Fahrenheit is equal to 9/5 T Celsius plus 32, and you can see there is no equal change. So if the Celsius, for example, changed with 1 Celsius, you will see that the Fahrenheit will change with a different value. It's not 1 Celsius. Let's erase what we have here so we can have like more space. Let's do so let's do now let's do now option B. So we know option A. In option B we have Kelvin and Celsius. It looks like this is the right answer. So why is that? If I have like here like 1 Celsius and I have here 2 Celsius, and I change the 1 Celsius to Kelvin, so I do 1 plus 273.15 Kelvin, and for 2 Celsius I do 2 plus 273.15 Kelvin. This is going to give me 274 point 15. Yeah, so we need to have some space for 0.15 Kelvin. I'm sorry, so just we need some space. And let's see here if we can have eraser. So the eraser, yeah, the eraser doesn't work. So maybe I need to clean the whole thing and just have more space here. So if I converting from 1 Celsius to Kelvin, so I will have 1 plus 273.15, and that's going to give me 274.15 Kelvin. And if I change from 2 Celsius to Kelvin, I will have 2 plus 273.15, and that's equal to 275.15 Kelvin. You can see the change here is 1 Celsius and the change here is 1 Kelvin. Okay, so we have 1 Kelvin as change, so we have 1 Kelvin as change here, and we have 1 Celsius as change here. So you can see the change keeps the same from Celsius to Kelvin. So B is the right answer. Okay, so C is wrong and D is wrong. Okay, and also A is wrong answer. Let's now move to the next question. I'm going to do now number 5. Which of the following represents the lowest temperature? In my class, all of you got the right answer, so it's minus 40 Fahrenheit. It is the lowest. It is the lowest temperature among all of these temperatures. Number 6. Which assumption is part of the kinetic molecular theory of gases? Let's check each one of them. So gas particles experience strong attractive forces. Gas particles occupy a large fraction of volume. Collisions between gas molecules are perfectly elastic. Gas molecules lose energy when they collide. Okay, so this is the assumption. So this is a consequence. They lose energy, so this is a consequence, but the collision between the gas molecules are perfectly elastic. So this is what do we have in the ideal gas theory. Okay, so we have all of the gas particles collide with each other with elastic collision. Okay, that's right. Let's see here. So number 7, when the temperature of an ideal gas increases, so the average speed of its molecules. So let's see what will happen. If the temperature increases, so what will happen to the speed? The thermal energy, guys, which is 3/2 K Boltzmann temperature, actually is proportional to the average velocity. So what you can see, guys, it's actually proportional to the average velocity squared. So by increasing temperature, you will see that the velocity of the gas particles, or the speed of the gas particles or the gas molecules, will increase as well. Okay, so we know this relation, guys, between the thermal energy and the average kinetic energy of the gas molecules. So now the right answer is B, which is increasing. Going to move to number 8. So in number 8, why do lighter gas molecules move faster on average than heavier ones at the same temperature? So if the gas molecules like have mix between like small molecules and large molecules, and at the same temperature, you'll notice them that they have the same energy. So what does that mean? That means that their masses are different. Okay, so we see this particle moving with a kinetic energy like 1/2 m1 v1 squared, and the second particle, which is large molecule or particle, for example, you will see it's moving with 1/2 m2 v2 squared. So we know that m2 is large and m1 is small. Okay, but even though m1 is small and m2 is large, you will see that the smaller particles will have higher speed, and the larger particles will have a lower speed. And this combination between masses and velocities will give you the same kinetic energy, which will give you the same thermal energy. That means the same temperature. Okay, so different masses means different velocities, but when we compare the kinetic energy for those two molecules or particles, you will see that they have the same kinetic energy. So C now is the right answer. They have the same kinetic energy, but just smaller mass. Okay, you can see that one of them has like smaller mass, but it has the same kinetic energy. In number 9, according to kinetic theory, gas pressure arises from. This is kind of a question that helps you to understand the origin of pressure, guys. And if you still remember the example that I gave you in my session with the container that has gas molecules inside and they are moving here and there and colloid, okay, and you still remember what happened, okay? So there's change in momentum, and there is pressure on the wall, on the container walls. So let's see. According to kinetic energy, gas pressure arises from gravitational attraction, molecules colliding with the container walls. So of course it is B. We have molecules, gas molecules, collide with the container walls. Now let's see number 10. I will double check that you can see number 10. I think I need to move number 10 a little bit up so you can see it. I'm going to erase all of this. Yep, like this. So we have number 10 right here, guys. So number 10, if a gas sample's temperature is doubled in Kelvin, of course, what happens to the average kinetic energy? Is doubled, halves, it remains constant, it quadruples. So what do you think, guys? We have here temperature, and what happens to the average kinetic energy? So we always write the equation like this, guys. So we have average kinetic energy, it's equal to 1/2 mv average velocity squared, and that's equal to 3/2 K Boltzmann temperature. If I double the temperature here, if I multiply the temperature by 2, I need to multiply the kinetic energy here by 2. So you will see that the kinetic energy, or the average kinetic energy, will be doubled. So you can see now A is the right answer. Okay. For number 11, Boyle's law states that at constant temperature, what will happen? Always we need to go to the ideal gas equation. So we have pressure times volume is equal to a number of moles times the gas constant times temperature. If the temperature is constant, we will have volume is equal to a number of moles times the gas constant times temperature, and then we divide the whole thing by pressure. Okay, So now let's go back and see what is the right answer. We can see here pressure is proportional to volume. Pressure times volume is equal to constant. Pressure proportional to temperature, and volume over temperature is constant. I can see here the number of moles is constant, the gas constant also is constant, and the temperature according to Boyle's law is constant. So you will see, guys, that the right answer is B, which is PV is equal to constant. So B is the right answer. Okay, let's move now to 12 and see what we can do with 12. So in problem 12, according to Charles' law, okay, what happens to gas volume when temperature increases at a constant pressure? We have the pressure, guys, is constant, so the pressure like never changed, it is constant. And according to the ideal gas equation, we have PV is equal to nRT. Let's check. So the temperature increases, so the temperature is changing. What happens to the gas volume? So the volume is changing, temperature is changing. So I have V is equal to nR over pressure times temperature. The number of moles times the gas constant divided by pressure, that's going to give you a constant number. So you can see now that the relation is between volume and temperature. And since we have now this relation between volume and temperature, so you can see when the temperature is increasing, you will see that the volume is increasing. So you will see that B is the right answer. For number 13, in Gay-Lussac's law, pressure is directly proportional to temperature when volume is constant, temperature is constant, moles are changing, volume is decreasing. Again, the equation of the ideal gas equation, we have pressure times volume is equal to number of moles times the gas constant times temperature. Okay. Pressure is directly proportional to temperature when the volume is constant. Okay, so it will be A. So when volume is constant, you will see that increasing pressure will increase, increasing temperature will increase pressure, decreasing temperature is gonna decrease pressure. Okay, so always, guys, use the ideal gas equation. It's very important. Can help you to understand all of these relations. Let's move now to number 14. And number 14 talks about Avogadro's law. It is a definition, so I'm assuming that all of you know this question. So what does Avogadro's law state? Equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. Here we have pressure is inversely proportional to volume. We have volume is inversely proportional to temperature. We have equal moles have equal masses. So the right answer is A. So this is Avogadro's number. Okay, so equal volumes of gases at the same temperature and pressure contain equal number of molecules. For number 15, at a constant temperature and pressure, if the number of moles of a gas doubles, the volume will, or is going to, let's see, doubles, halves, remains the same, became 1/4. Let's see. We have the ideal gas equation, so PV is equal to nRT. We have a relation between pressure and number of moles. If the number of moles of a gas doubles, if I multiply in the number of moles by 2, so what will happen? You will see that the pressure also will be doubled. Okay, so A is the right answer for number 15. Okay, Let's now move to 16. So 16 is not, yeah, it's not complicated. So you can see the answer is pretty clear. The ideal gas law combines which individual laws? I have here like Boyle's, Charles, and Avogadro's law. I have here Ohm's, Newton's, and Coulomb's law. And here we have Pascal's law, Hooke's law, and Bernoulli's law. Here I have Dalton's, Charles, and Coulomb's law. So D, C, B are wrong, and A is the right answer. Okay, for number 16. For number 17, which variable must be expressed in kelvins when applying the ideal gas law? Yeah, it is straightforward, guys. So of course the temperature needs to be converted to Kelvin. Okay. Let's move now to number 18. If the pressure of a gas is tripled while its Kelvin temperature remains constant, so the temperature is constant, what happens to the volume? Again, from the ideal gas equation we have PV is equal to nRT. The temperature is constant. Here we have the gas constant. Here we have N, which is the number of moles. It is constant. You will see now that the relation between pressure and volume will be like this. So pressure is equal to N RT divided by volume. If the volume is going up, you will see that pressure is going down. If the volume is going down, you will see that the pressure is going up. Okay, so it is inverse relation. If I, for example, triple the pressure of the gas, so if I have here 3P, I'm going to write that down here. If I have like 3 pressure, it's equal to nRT divided by volume, and that will give me pressure is equal to nRT divided by 3 volume. So you will see, guys, if I treble the pressure, I'm going to play with this equation a little bit, so I can have here volume is equal to nRT divided by 3 times pressure. Okay, if I multiply the pressure by 3, so what will happen? You will see, guys, that the volume will be 1/3 of the original volume. You can see that from this equation. And also I can erase the whole thing here and show the equation for you. So we have here PV is equal to nRT, and from here we have volume is equal to nRT divided by pressure, and then if I multiply the pressure by 3, so that's going to give me volume is equal to 1/3 nRT divided by pressure. So that's going to give me the original volume value multiplied by 1/3. So you will see now C is the right answer for number 18. For number 19, which of the following best explains why gases are compressible? Okay, so it is straightforward also here. So gas particles have very little mass. I don't think this is the right answer. So gas particles are far apart with mostly empty space. This is the right answer. So gas molecules attract strongly. So gases are heavier than liquids. So B is the right answer. So between the gas particles or gas molecules, there's like a huge space, and that's why we picked B for number 19. Okay, so we are done with the practice conceptual questions. I will go now to the practice problems for chapter 13, and then I will go and start the practice problems and questions for chapter 14. Okay, so see you in the second recording, guys.